Our next topic is Pn Junction Diode. Now, what is Pn Junction Diode? How is it made? Let us discuss these things first. So, you know what is P-type semiconductor and what is N-type semiconductor. When you have P-type as well as N-type semiconductor within one single block, okay, then you can say that is a Pn junction diode. Now, where this junction terminology coming from, what is the meaning of that? That we will learn in this particular video. Okay, so because these are very important things, let me write them down. So how is a Pn junction made? So to answer that question, we can simply say that, okay, a semiconductor block, that means a pure semiconductor block is doped, okay, with third group and fifth group impurities on either side. So you take a block, one side you dope with the third group impurities, the other side you dope with the fifth group impurities, okay, to make a Pn junction diode. It's as simple as that. Please don't ever think that a P-type semiconductor, N-type semiconductor is joined to make a Pn junction diode. That is wrong, because even if you join whatever welding you do, the gap between the P side and N side will still remain, quite large compared to the atomic size, and it will never be a proper Pn junction diode. The only way you can make a Pn junction is by doping a single semiconductor block, with the third group and fifth group impurities on either side. That is the only way. So to schematically show the same thing, so you take, just a moment. Okay, we consider a semiconductor block, and as I told you, we dope one side with the third group elements and the other side with the fifth group elements, and eventually it becomes a Pn junction diode. Okay, so the original block is something like this. Since we have made one of the sides as P type, okay, by doping it with the third group elements, so I will color it differently, and the other side I'm sorry, one moment. It is better that the N side is colored blue, just it looks better, and this side is P. Please understand, these are not two blocks kept side by side, but they are two sides of a single block which are turned P and N separately. Please understand, as we have discussed earlier, on the P side we have holes in majority. So there are electrons also on the P side, but majority are holes. Okay, remember that. I am drawing very few of them. There are trillions and trillions, okay, or even more than that. Okay, and similarly on the N side you have electrons in majority. I am drawing very few of these carriers. Actually, there are billions of these within a millimeter size also. Okay, within every millimeter you will find billions of them, hundreds of crores of these holes on one side and electrons on the other side. Okay, it is very important for the students to realize that the numbers we are talking are very, very large numbers. It's essential, okay, and it will be helpful, okay, in some of the things that we are going to discuss. Now, what happens very close to the region where the P and N type semiconductors are coming face to face with each other? So the junction is very simple thing. Wherever the P and N type semiconductors meet, okay, that is nothing but junction. So on either side, you take few millimeters, okay, or even actually few micrometers, and that region is the junction. Okay, now at this junction, what actually happens? That's what is our primary discussion. So first of all, please understand. Let me magnify this small region and show it to you. So please understand, we are taking a very small region, okay, comprising of few lakhs of layers on either side, okay, or few crores of layers on either side. That itself is within few micrometers or millimeters, not more than that. So within that very narrow region, what is happening is what we are trying to discuss. So if I magnify and see it, so I'm drawing them big because I have to explain some of the things to you. That's why. So please understand. So at the junction, what happens is that, as we have already discussed, there are many holes. I mean, holes are in majority here. And electrons are in minority. Similarly, on the other side, you have electrons in majority, holes in minority. Sorry. Okay. Now, so if you go from one side to the other side, P side to N side, the number of holes is very, very high and suddenly it drops to a very low value. So very high number of holes and sudden drop to very low number of holes. Or if you talk about electrons, very low number of electrons and suddenly very high number of electrons. So concentration of holes, if you go across the junction, suddenly drops, or concentration of electrons, if you go across the junction from P to N side, suddenly increases. Okay, so near the junction, there is a change of concentration. You take any of the carriers, either holes or electrons, there is a sudden change of concentration of those carriers. The change is nothing but called, scientific terms, it's called as gradient. So, I mean, whatever the change being with, occurring with that distance or whatever, that is called gradient. So you have a concentration gradient at the junction. This is a very important term. Students must remember this term. So let me write here. There is a concentration gradient across the junction. This gradient is what we have created by doping the two sides separate differently. Okay. Now, basically, it's not like P side has no electrons and it's not like N side has no holes. Both sides have both of them. On the P side, very high number of holes and low number of electrons. On the N side, very high number of electrons and low number of holes. That's what it is. And both sides actually, they allow for both holes as well as electrons. Now, what p sides will feel? It feels that the electrons which are in minority on the p side feel that, oh, there are so many electrons on that side. Why can't they jump here? Or basically the holes and electrons are like, although they are not really opposite poles, but they also have that affinity towards each other. So the holes on p side attract the electrons on n side. Okay. And therefore, what happens is that the electrons, because holes are basically, they are not really physical entities. They are just absence of electron. Okay. That covalent bond is called hole. So it's the electron that moves from n side to p side. That basically is diffusion. Why? Because the concentration of electrons is very high on n side and very low on p side. There are many holes here which have the affinity for electrons. They can attract the electrons. I mean, if the electron goes and falls in the hole, the energy level decreases and accordingly some energy is released. So it's a favorable event energetically. So concentration gradient causes diffusion of electrons. And when electrons move from this side to this side, that's called current. Basically, electron movement is called current. So diffusion current. So this is a very important factor. Concentration gradient causes diffusion current. As you already know from the chapter of current electricity, if electrons go in one direction, we say the current is in the opposite direction. Current is opposite to the direction of motion of electrons. So diffusion current is from p side to n side. Remember that. Okay. I mean, electrons diffuse from n to p, but diffusion current, if you want to say, it is from p side to n side. It is from p side to n side. So diffusion current is caused due to concentration gradient, and it is from p side to n side. So in this particular video, we have discussed about how a Pn junction is made, and we have discussed about concentration gradient, and this concentration gradient causes diffusion current. Now, what happens due to this diffusion current? Will it continue forever or will it stop? Is it self-restricting type of thing? Okay, and so why is it self-restricting type of thing? And what happens? Is there some other phenomenon that starts? These all questions we will address in the next video. Okay, thank you.